Hello everyone, it's April 16th. Alright, let's get to it. No wasting time, let's get to it. My cat is by my foot, he's trying to bite me. Alright, remove all adjacent duplicates in string. Number 2, given a string, okay, k duplicate removal consists of choosing k adjacent and equal letters from S, k adjacent and equal letters from S. Did I just repeat that sentence? And removing them, causing the left and right side of the deleted substring to concatenate together. Okay? We repeatedly make k duplicate removal on S until we no longer can. Return the final string after all such duplicate removals have been made. It is a guarantee that the answer is unique. No adjacent duplicates, so nothing to delete. 3, we can delete EEE, and then CCC, and then BB, DDD, and AA. EEE, then CCC, we get this. We delete BBB, we get this. Okay. Okay. String manipulation, one of my least favorite, but let's take a look, see how this one can be approached. So I like the second example, so I'm going to write it out. E, 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 D, B, B, C, 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 B, D, A, A. So removal definitely will turn that into a list, right? And then 3 consecutives. So sliding window, 3 at a time. And we found EE first. We can turn them into empty, like empty string. CCC will become empty string, or like, yeah, it'll become empty string. Then what? If I do it again, how do I avoid these empty strings? So instead of thinking, yeah, I'm just checking myself. Oh, but K can be huge, right? K can be huge. K can be huge. I mean, we can like remove it, turn it back into a string, and run it again. Yeah, that definitely works, but I don't think that's very efficient. Let's see. What is I'm gonna try. I think it's gonna time out if we do it the naive way, which is, each iteration we will turn that into a string with all these things removed. So we have to do on. That is, turn that into a list of strings, a list of letters. We convert those into empty, and then we merge them again. In the next round, we expand it again. So we turn to list, and at the end, turn back to string, turn to list. That's all on, right? But how many times you have to do this? Well, you have to do it, I don't know how many times. I mean, maximum will be hard to say how many times. But we can try, right? Yeah, I mean, even if it times out, it's fine because that's a correct solution, right? It's a correct solution, and we can use that for our testing purpose. So I think it is a good idea, even just to try this naive solution. I mean, who knows? Maybe we pass. If we pass, then we will be more confident, more comfortable thinking about a better solution. All right, so this one runs the risk of timeout, but that's all fine by us. We're gonna call remove duplicates, right? So we have S, and I probably need a. I guess it's fine. So we're gonna have origin length. I'm gonna call it len s, right? And then I'm gonna say while true. So s, we're gonna say s list equals s dot split dot list s, right? Split it, and then I'm gonna say, oh no, this is going to time out because we have to check each single one of them. Like every single one of them, we have to check. That is not looking good. Like it has to be k times s, right? K times n, because every time when you check, you have to check one by one. No. That's not the way to go. We need to read through this. We're gonna find adjacent, right? We're gonna find adjacent and to see if it fits. If it fits, then we remove. Man, how do we do the removal like fast? So yeah, we cannot do the window thing. Then we do window thing because this k can be huge, right? So we have to check every single one of them. Move on, check every single one of them. No. We just read through, do pairwise comparison, and if it's the same, then we just keep a counter, right? They're all the same, keep a counter. When they're not the same, then we know how many there are and what there are, and we are going to, what are we going to do? Well, we can build a new string as we go through. Like if these two are different, then definitely we'll push this into the new string. And then, well, not really into the new string. I'm not sure which one's faster, but I think it's fine. We push this into a new string. And then next one that is equal, then we hold. And then equal, and we have a stretch of equals, so we know how many there are. And then if it's larger than this, then we can remove, and then we push in whatever is left, okay? And then check. That might be a better solution, right? That might be a better solution. And we don't have to turn this into this yet. We're gonna say ns, right, next s, wanna build it. And then we're gonna say for, oh, I don't even need this. Oh, I do want to, no, we don't need this. So I'm going to say for s, no, for I, letter in enumerate. No, that's not a way to go. For I in range, len s minus 1, right? And then we say if si is not equal to s. Hold on. We have to also set the repeat. So the current count set to 0. So if it is equal to si plus 1, right? If these two are equal, then count has to be 1. Then count plus equal 1. So we find like this situation, they're equal, so count plus equal 1. And then we'll see the next one, and then count plus equal 1. Until we say else, if they're not equal, right? If they're not equal, then we're gonna check, right? Then we're gonna check what? We're gonna check to see, oh, not only do we need that, oh, we actually don't need, we don't need a position. No, we have the count, and that's good enough. So when it's not equal, right? So like this situation, then si pointing to the repeating one, and this pointing to the next one, which is fine. So pointing and repeating one, when they check, right? If count is larger or equal, and we call it larger or equal to k, right? If that, then we're gonna say additional, and say AD additional shall equal to count minus k, right? Count minus k and times si, right? So that is this much of empty string that we need, a string that we need to do. We have a small question. Just want to see if the syntax is correct. So 3 times, let's say a. Okay, how about 0? It should be empty string. Yep. So that's fine, right? So additional is here. If count is smaller than if count is smaller, so else if count is smaller, then we just do count times si, right? And once we finish that, we need to say ns plus equal to add additional. Now we also need to reset count if count is not. Yeah, so once this done, when count reset to 1, and this one we can write in one line actually. So I think we can do it this way. All right, this else count times si, right? Okay, so we update string and then do this. Right, after we all done, right? After we all done, so the last two compare, and then we come out. Right, we come out. Then we're gonna compare one more time. Yeah, we're gonna do one more time. We're gonna do this one more time, and then ns plus equals to ad. Yeah, one more time, because at the end we might not have something to compare to. So at this stage, we have the new s ready. Now we're just gonna swap. All right, we're gonna swap. Not really swap. We're gonna say s equals new s, and go back up. All right. But we need to know when to break. Well, it breaks if it's nothing changed, right? So when we say if ns equals to s, then we break. Otherwise, s equals this, go back up, and then we redo this. We're gonna return s, new s, doesn't really matter which one. Okay. All right, let's give this one a shot. So we're gonna start with ABCD, which give us ABCD. Oh, we also need K, so 2, K is 2. Next one, I have to put this one all in. That's 3, return AA. Next one is this. And then K is 2, give us PS. Okay. So we have S, K, answer. This is remove duplicates, S and K. And then string index out of range. Oh yeah, it is. Hold on, why is it out of range? Why is this out of range? I shall end with len is -1, right? So which is -2, right? Minus it x is will len with it shall exit with the correct I, and then I'm just trying to do this, and I say line 17 out of range. Let's see. It's actually the first one, right? I think the first one is out of range. Yep. Why is that? So count is 1, going inside, so it's 4. This one's 3, so 0, 1, 2. 0, 1, 2, yeah? And then we say this and this is equal. Nope. Then additional will equal, so count is 1. Is smaller, so we do count times si, which is a. We'll add it to it, count equals 1. Right back up. Next one, we come to BC, so add a B. Next one, CD, we add C. Next one, well, CD is actually the last one. CD is the last one. And then it's now good. Come up. Okay. If I come up, so currently I'm at C, right? It will stop at C. So when I come out, it's actually at C. It's actually at C. So I wanted to stop at, so I have to be like this. So while I smaller than len s minus 1, right? And then we do blah, 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 and at the end, I plus equal 1, right? And then we will exit when I is equal to ln s minus 1. And then, yeah, this one shall be right. Okay, test these two. They all pass. Look at this. I am not very confident, but let's just at least give it a try. See if anything we can do to make it faster here. Guess that's about it. It'll be nice if we can have NS up there, right? And we have to reinitiate NS here. That's fine. Let's just do it. All right, try it. Let's see. So what we get. Pending. Oh, we got accepted. That was surprising. I thought this is a bad solution. It is not a good solution. It is not a good solution, but we got it. But it's I think there are better ones. All right, let's see if it's possible for us to make this look a little bit nicer. Ah! All right, so here, what we can do, can we move this one up? Like I was trying to think about if we can move this one up. I guess if we say while ns is not equal to s, right, and we initialize ns on the outside, like we did this, ns is not equal to s. And then we have to initialize ns on the outside, and then come in, it's not equal, and we reinitialize it. What if we don't initialize it here? We run, and then ns doing all this. Yeah, we still have to initialize it, but we can initialize at the end. All right, so we can also do a trick. All right, so we can do like this, and then coming back up. Oh, the ns will forever not equal to. Cannot do it that way. S equals this. Yep, we have to do it again. This also looks ugly. But, oh yeah, and then this is not correct. Oh yeah, it is not correct because, can't even change it. All right, we just have to go the Original route. Yeah, I see why. Yeah, it has to be this way. Oh, this one has to be true. We run a forever loop and then we make changes here. Okay, I'll just write a summary and check other answers. So the idea is to check, to do pairwise check. To pairwise check on S count. So each time, so count how many letters are in a consecutive, I don't think it's called consecutive, adjacent, in a adjacent duplicate. Once we get the count, we compare it. We know only count minus k of that letter can pass on to the next level string. At each level, we create a new string by accepting count minus k duplicate letters from the previous string. We end the loop when the new string is the same as the old string. All right. So the runtime depends on how many times we have to. I mean, the inner loop is on. The outer loop depends on how many times we need to run the deletion. So I actually don't know. What's the worst case? Worst case is each time we delete 2 and only delete 2. So the worst case is each time we delete only 2. And then the outer loop runs in O, I think it's for every time -2, -2, -2. So O and divided by 2 time, which means, this means in total, the worst case is O(n) squared. And we run at 108 milliseconds, which is 17% ranking. Fitting my description, right? Mediocre, pretty mediocre. All right, let's take a look at the hint. There's a stack to store the characters. When there are k, same, delete them. Okay. To make it more efficient, use a pair to store the values of the count of each character. I mean, it's the same idea, right? It's the same idea. I mean, pairwise is the same, but we just don't use a stack. Oh, a stack is, yeah, a stack is better. I think from programming perspective, let's try it. Let's try the hint using a stack. So stack, I want to say, what do we say? While true, right? And then stack equal is this. I'm going to say for for should I turn the S into old, like old stack and new stack, right? Yeah, we're gonna say like old stack equals S, so be letter, and it's 1 for letter in S, right? So this is old stack. And then this is going to be new stack. And we say for letter count in old stack, if not new stack, or new stack minus 1, 0 is not equal to letter, then new stack dot append append. So I can use tuple. I like to use tuple for this. The new stack, we're gonna append letter count. Right? There's no change. Else, which means we have a stack, we have a stack, and the top of the stack letter is the same. Then we want to change the value, so it has to be mutable. Yeah, have to be mutable. All right. So now I'm gonna say, so it's the same. So new stack minus 1, 1 plus equal to count. All right, now I'm gonna check. I'm gonna check if new stack minus 1, 1 is equal to k. So we're building them up. If it's equal, actually, it should be say like larger or equal to k. Yeah, larger or equal to k. Then what do? We're gonna say new stack minus 1, 1 minus equal k, right? And then we say if it's actually, we're gonna keep pushing. All right, we can keep pushing. I mean, it's fine. No, I want to pop it here. So, and then we just say if not new stack minus 1, then new stack dot pop. All right. And plus C, and then check if it's larger than k. If it's larger than k, we minus this, and if it's not, then we pop. Yeah. So after we run through the old stat, we're gonna say what do we say? We're gonna compare, right? And compare if they're the same. Maybe there's a better way to do it. So like if we run down, there's no popping, then we know that it's fine. So anyway, so old stack has to equal to new stack, right? And we'll go back up. But then every time we run this, we also need to say has pop, right? Has pop. It's not going to be false. And then every time we do this, we say has pop. It's true. And then at the end, I'm going to say if not has pop, right? Then I'm going to break it. Now after we break it, we know, right? If we break it, we know that the old stack, new stack should be the same. So we can just do new stack, right? We do new stack. So when I return, we have to join. Oh, that would be interesting. So we may have to say join. What's this? This is going to be letter times C for LEC in new stack. Okay, let's run it. It pass. So I don't expect. I think this is a. Isn't this like about the same solution? No, I don't have to run it. I run it already. All right, let's check it. Yeah, yeah. I think it's a similar solution. Oh, look at the runtime. Maybe there's a better way to do this. I mean, I don't know. I mean, anyway. So this is this comes from the hint, right? This comes from the hint. Using a stack. All right, let's check other people's solution. They may have better ideas. Problems. I think it's a medium. Yeah, it's a medium. Yeah, it's this one, right? Remove all adjacent. Yeah, I think this one. Yeah, I don't think it's easy. Yeah, this is a medium. All right, let's see. Have I done before? Nope, not done before. 2 pointers in a stack solution. 2 pointers. And the stack. Oh my god, look at this. Stack equals C equals 1. If it's equals K, I pop. Else, we do this, join. Hold on. Oh, you don't have the break? For C and S, stack equals C. We do this. If it's K, then we pop. Yeah, that's exactly what is here, right? A plus equal 1. And then pop, else stack.append. But you only run it once. Oh, it did not run it once. No, because as the stack falling back onto itself, it will get removed. You don't have to have the while true. It basically just run it once. Yeah, I only run once. Because you have 3, that's the same, and then they got removed, and then new one comes in, and when new one comes in, the top will get changed. It's like one of those games, right? Yes. Yes, good. So we just make a little bit change. And we don't have to do this as well. We just need only need one stack. All right, and then do solution 3. Let's try now to look at it. Solution 3, yeah, that is the official solution. Yeah, I know. So this is the official use of. So we just need a stack, right? And then all we need is a sentinel. And then for lettering S, right? Every letter come in, and I'm going to check if stack and stack top of the stack 0 is equal to letter, right? So equal to letter. Then we say stack minus and then 1 plus equal 1. So we have a new letter come in, and then we check if stack, that's not L, that's K. If stack, top of stack, is equal to K, then stack dot pop, right? And that's it. Else, it's not equal, then stack dot append letter and 1. And at the end, when I return, I think that's the same thing. Letter and stack. Yeah, that is the official solution. Yeah, this is the official solution. All right, this is official, not official. This is the stack solution from Lee 215. Much, much better than the one I conjured up above. The key idea is that each time some letters get popped, new letters fall on top of the stack, and we can, on top of the stack, and we can continue removing. We can continue removing without, continue removing, how should I express this? Continue removing, this is hard. The key idea is that we only need to iterate s once, because for example, once, right? E.g., given say A, B, 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 A, all right, and K equals 3. After we remove B, 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 we don't have to wait until the next iteration to remove A, but we can remove A right after BBB is removed, because the last A falls on top of the stack, sees that we already have 2 A's, and immediately merge with them and gets deleted. Therefore, the outer loop is unnecessary. Yep, this one is much, much better. This one is also going to be faster because it takes less time to initialize. Well, not even initializing. Yeah, this is the official solution. I think I'll be faster than this, maybe even faster than this. Yeah, there we go. That is the one. 96. See, but this is the official. Okay, he also posted a 2-pointer solution, which is this. Does that mean we only need to do it once as well? Well, I don't really know. Let's see. 2 pointers. Oh, we still have a stack. Oh, decent. Cannot solve this one easier. So just this stack to array. So we have I and j. Stack I equals stack j. Count I equals I larger than 0, and stack I minus 1 equals stack j. Then count, is a count another thing? Okay, count is another thing. Then count plus 1, elsewise 1. If count equals k, I minus equal k. Hold on, there's some magic here. So initialize, would say stack I equals stack j, and count I is in the ith position, right? Equals this, right? We check this, I larger than 0, and so I larger than 0, okay, and I minus 1 equals stack j. Stack I minus 1 equals stack j. If they're equal, then it's going to be count I minus 1. It's the previous count plus 1. Count I equals the previous one plus 1. Otherwise, it's going to be 1. And then if I equals k, then I go all the way back. So I and j are index, right? Indices. And then every time we're going forward, I will be pointing to the current front. Yes, so stack from 0 to I contains the final result, right? Contains the final result. And then as we keep, and j is iterating. J is iterating on the s. So every time I is always at the front. I is like one position past the end of the final string. So every time we find j, we always do this, put the j down, and then count is another array, which is counting at ith position, the number of adjacent duplicates that have been accumulated. So we need to update count. So how do we update count? We're going to compare stack I with stack I minus 1. If it's equal, then count I will equal counter I minus 1 plus 1, yes. And then we check count I. If count I equals k, that means we have to remove them. So we move I forward, backwards. Well, move it left, right? Move it left k times. Nice, nice, good solution. Wow, very good, very good. Oh, I think I uploaded already, right? ON for one pass. This is some Chinese thing. Yeah. All right. Let's implement it. The two pointers, right? So let's say the two pointer solution also from Lee 215. Very brilliant this solution is. All right, let's try it. So what we're saying is, I call it stack. I don't like to call it stack. I like to call it rest list, right? Rest list is going to be this. Probably not. Rest list has to be a this, right? Times, all right, we didn't do n equals len s, so it's going to be maximum is going to be n, right? So that's the rest, and we need a count. Count will be 0, right? 0 times what? Let's see. So count equals this. I think it should be count is 1. So everything starts with 1. All right. So I have count, we have 0, and then when I have I, j. So I only I equals 0. Then we say for j in range n, right? And always every time. So I will be pointing to the front at the beginning of the, yes. So we're gonna say rest list I is going to equal to sj, right? And then when we do that, then we're going to check. We're going to say if I is larger than 1, no, I is larger than 0, then we're going to check if they're the same. If they're not the same, so if this and rest list I is equal to rest list I minus 1, right? If they're equal, then we say count I equals plus equal, no, just equals count I minus 1 plus 1. Right? At i's position, the count is incremented. And after that, we're going to check and say if count I is equal to k, it means we have accumulated. Right? We have accumulated that many items, so we need to remove it. So I has to go 1, right? I is pointing here, 1, 2, so I has to go back, right? I have to go back. Do I go back k times? So if 0, 1, 2, 3, right? And I is 3, count I equals 1, 2, 3, then if I as 4, right? It's a 3, 0, 1, 2, 3. 3 minus 3 is 0, so we're going back. I actually don't think it should be minus equal k though. Because if a minus equal k, now we're now pointing at the front. We're replacing stuff. Actually, I think it should be k minus 1. That's my current understanding. It should be k minus 1. Because we want the I to be pointing at the front, so we can always add new things into it. Yeah, that's my understanding. So we're going to finish, right? After we finish, what we're going to return is basically dot join rest list to I, because I will always be pointing at how do I increment I? We have to increment I, right? Yeah, so every time if it's larger than 0 and if it's not, then I has to plus equal 1. Because I plus equal 1, that's why we don't have to do this. I always have to plus equal to 1. I always have to move to the next position. And I think that one shall work. Oh, did not work. All right, let's take a look. Rest equal to sj, that's fine. We deleted this. It's weird. I larger than 0. The rest equal to, that means these two are the same. And the current equals previous count plus 1. And if current count equals k, then we go all the way back. If it's not equal to k, then we just keep adding 1. Yeah, I think it should be fine, right? It's the same. And then, all right, we're gonna have to take a closer look. All right, so what do we want to see? We want to see at the beginning. No, I want to see at the end before incrementing. So we're gonna print sj, the current, and a rest. Okay. So sorry, d, e, e, oh, and also count. Okay, so initially everything is 1 as expected, and then we have E, that's 1, and now EE, so there's a 2, EE that's 3, right? And then because it's 3, I go back, so next D is here, that's correct. It's D, it becomes 2, and then it's B. Oh, it shall be 1 here. Ah, yeah. So if it's this, I see. So count I equals count I minus 1 plus 1 if this, else 1, right? Have to do 1. And, can't wait, I have to do it here. Don't do this, then we pass. Yes, this is the 1. And, yep, then we pass. Oh, nice. Very smart. Let me write a few more. The key is to keep 2 lists. One storing the final outcome, and the other is stores the number of duplicate adjacent. How do I spell it? Adjacent duplicates, right? The other one's the number of adjacent duplicates at each position. Note that the position in the final outcome list and the count list is corresponds are the same. The positions in these two are always the same, but they are different from the position in S. As we iterate through S, we use pairwise comparison to determine whether we have encountered sufficient number of adjacent duplicates, right? So we find that. Once that is achieved, we move the index of outcome list k steps to the left. This is equivalent to deleting those duplicates. We make sure that the index of the outcome list always points to the points one step ahead of the current end of the outcome string, right? One step ahead of the current end of the string. Yep. And that's about it. Yep, that's about it. Let's run this. So we run 4 solutions, and yeah, these are better solutions. So this one 4, which actually means, because if we're receiving like similar runtime, right? We're receiving similar runtime. Not really similar runtime, but this I think is O(n) squared. A worst case is O(n) squared. A good case is probably also close to O(n). But this one's slow, that's for sure. And this one's very slow. These are good. They only run it once. Yeah. All right. Yeah, this O(n) solution is better. All right, that's it. It's a good question. Very good question. We did solve it, but it's it's not really a good solution that we use, because we have to constantly creating new strings and we have to loop like over many times compared to the ones that's that's the official one. The official solution, the stack one, is really good. We didn't really quite got it when we first saw the hint. I mean, this one is kind of there, kind of now. We didn't really completely get it. And this is the real deal. All right, that will be it. That will be it for today. I will see you guys tomorrow. Adios.